final presentation for CSIC 5001. So me and my colleague Neel, we are working together on this project. The topic of our project is segmenting cracks using classification algorithm on low dimensional embedding of crack dataset. So at first I will discuss about the background and the problem statement and the data collection and pre-processing that we have used. Then Nilkant will be discussing about the methodology and the results. Thereafter, I will be discussing conclusion and what are the future direction. I think many of you does not know about concrete and how it fails. Here are a few snapshots from the accelerated test. As you can see, with increasing time, there is some formation of cracks. As a result, the structure loses its strength, leading to the failure. How can we stop such a thing? And there have been few proposals about it. One of the most common proposal is to, if we collect a lot of data set and label those data set and train a CNN, then we can test on any such surfaces and find out where the crack is, and we can report those cracks for engineers to repair such a structure. But the key point of using such a classifier is having a labeled data set. The problem is very new. And to label such a data set, we need some expert, which is expensive, which is the motivation of our work. And we use embedding or use an alternative to use learning. So next, I will discuss about the data collection. The data collection is from various tests performed in a materials and structure laboratory, and from all the experiments, to crack formation or the damage formation during the accelerated test were captured through various cameras, and all those images are divided into subsets of 227 into 210. They are then transformed into grayscaling and annotated and flattened to create a crack dataset IN cross D. N is the number of such segments is 10,000, 5,000 classified as damage, and 5,000 classified as not damage. And this is the dimensionality of the set as it's 227, 51k, 51k. So here are some examples of such a data set. As you can see, all the data sets are unique. There is large variation between them. So next Kundu will discuss about various dimensionality techniques.
Hello everyone, my name is Neel and now I will present the methodology of our project. First I will present the dimension reduction techniques which we have explored in our project. First we use linear dimension reduction technique like PCA and MDS, which can be found by using the single value decomposition of the center data matrix Y as shown here. The top k right singular vector give the PCA and the top k left singular vector give the MDS embedding, which are the dual of each other. MDS tries to preserve the Euclidean distances between the data points. Then we use a non-linear dimension reduction technique like isomap, which tries to preserve the geodesic distance between the data points and assumes that the data lies in a high dimensional manifold. From the data, first a neighborhood graph is calculated, and from the square distance matrix, the kernel is calculated, and the spectrum decomposition of this kernel matrix gives the isomap embedding of our data. For the nearest neighbors, isomap approximates the geodesic distance with the corresponding Euclidean distance, and for the faraway point, the shortest path distance is calculated to approximate the geodesic distance as shown here. And then from the square distance matrix B is calculated, which here H is the householder matrix, and the eigenvalue decomposition of this B matrix and taking the top k eigenvectors and eigenvalues give the isomap embedding of our data. Then we explored TSNE, which is a very efficient algorithm for 2D embedding and for visualization that uses a probabilistic distance between data points. In the original space, it assumes the probability between the data point as a Gaussian distribution, which depends on the Euclidean distance between the data points. And in the low dimensional space, it uses the it uses the student's T distribution to model the probability between the low dimensional data points. And this T distribution helps to prevent the the problem of crowdedness in the low dimension. And in the optimization problem, the KL divergence between these two distributions P and Q is minimized to find the low dimension embedding using stochastic gradient descent. Then we use different nonlinear and linear classification algorithms on the low dimensional embedding of our data set. Specifically, we use a 2D embedding of our data and then use these classifiers like logistic regression, ridge classifier, k nearest neighbor, SVM with regularized radial basis function as the kernel function, and the decision trees and deep neural network. These are the 2D visualization results of our high dimensional data on the 2D plots. So we use PCA, MDS, isomap, and TSNE on our data. Here yellow correspond to the data point which have cracks, and purple which correspond to zero, they don't have any cracks. Although in this project we would like to use other nonlinear dimension reduction techniques like Hessian LLE, LLE, and LTSA, but we found that due to the very large dimension of our data, which has 51 dimension data, we were not able to run those algorithms on our data set. Hence, it is left as a future research direction where efficient implementation using the GPU acceleration can be used for implementing those algorithms such that it can handle the large dimensional dataset like our real dataset. Here we see that none of these algorithms can efficiently separate the two classes into two different clusters. Hence, now we use different nonlinear and linear classifiers to classify these data points. So here we present the classification result of the low dimension embedding of our data using different classification algorithm. Specifically, we find that only non-linear classifiers like k-nearest neighbor, SVM with radial basis function, and deep neural network give the best accuracy and the precision on the data. As we have seen in the previous slide that the low dimension embedding on the data is not linearly classified. Hence, logistic regression and ridge classifier perform poorly, and only non-linear classifier give good accuracy on our low dimension embedding.
In real life, there are many hyperparameters which could affect the result. Two of those parameters are or hyperparameters that are important choices are ordering of the dataset, because we cannot control how we are receiving the dataset. With a Monte Carlo simulation, by changing the order of the dataset, it was found that the performance, accuracy, and precision is not affected by the order of dataset. This is because the spectral roots is not affected by changing the rows of the distance matrix in MDS. Similarly, there is another important choice: how much dimensionality should we keep in order to build a classifier which has maximum separability. To identify this, also performed a control test by increasing the k, the top eigenvectors, and measure the performance. And it was found that separability decreases with increasing dimension when the k increases after 5. I think this could be because it does not include the factors which can segregate the damage with the non-damage, or maybe they can also include some kind of noise which results in a classifier to have much worse performance than before. Apart from the sensitivity result, we can use MDS to do some more interesting work, such as ordering of images. Ordering of images in which we just input a random set and we organize that set based on the topmost eigenvector, and we can get an order. If we repeat this process for non-damaged set, we can order the images based on the brightness, which is visible to us. But the brightness is related with the discoloration of the concrete. A less bright image, that is a darker image, is an example of concrete with higher quality or higher strength, and is expected to have a higher lifespan. Similarly, a concrete which has more whitish color that is of less quality, or it has been used for some time and it has less service life remaining. Similarly, if we apply the ordering of images for a damaged dataset, we can see that such an order faintly reflects the total amount of damage. The total amount of damage is the damage consisted within the crack. So what is the volume of the area within the crack? This is a reflection of how important is now to do the repair. The one which has a higher volume, we need to do repair as soon as possible, while one which has a lower, we can wait for some time to do the repairs. So we can see that not only MDS can do classify, but also this can be used to gain some interesting insights within the image, like a different type of damage, such as discoloration or the amount of damage. So here are the final conclusion and future direction of our research work.
In this research work, we applied various dimensionality reduction techniques to segregate damaged and non-damaged images. It was found that for MDS with some non-linear classifier produces best accuracy and precision for our dataset. For this classifier with increasing dimensionality, accuracy of non-classifier decreases. However, ordering of images does not have any such effect. It was found that ordering of D images with MDS produces a fainter correlation with the amount of damage. However, such an order for ND images re reveals discoloration in the concrete surface, which is related to the quality of the concrete. Other non-dimensionality reduction techniques such as LLE, HLLE, and LTSA could not be applied because of high dimensionality of our dataset. In the future, we will try out more exhaustive selection of embedding technique and classifier for our dataset for better results. Thank you so much.